Welcome, Algebra 2. This is Section 3.4, Linear Programming. The essential question is, what is linear programming? So let's begin. What you've already learned, let's go over this. You've learned how to graph equations, you've learned how to graph inequalities, and you've learned how to graph systems of inequalities. Now, linear programming is kind of the next step into this. And basically, you graph several inequalities together and you form a shaded region, and you can do stuff with that. This is where a lot of this math actually gets practical. This lesson is not going to get into much of the practical side, but it's just going to show you the function behind it, and then we'll do the practical side more in class, because that's hard to show in a video. Anyways, this is how you do this. So here's what's forming. I have a system of constraints here. What's a constraint? Constraints are inequalities that create the limits of the graph. So I have 4 different constraints or 4 different inequalities, and I use that to form a graph. And then after I graph all those, I get this little region right here. We call this it's a little polygon here. We call this the feasible region. This is the shade, and this is the area we actually shade. It contains all the points that satisfy the constraints. So basically, all my possibilities for x and y are right here. All the possible points that will be valid for these constraints. So let me kind of demonstrate how these were graphed. So first one, x is greater than 2. So that's going to be straight up and down line right here. I'll do these in red. And it's going to be greater than is going to be dashed to the left or to the right. So I'm going to put these little tick marks. Now the next one, y is less than 3. No, it says y is greater than 3. So greater than 3, it's going to be a line straight across just like this. And greater than means I'm going to do tick dashes above it. So I'm going to tick dash above just like this. Now the next one says y is less than 6. Less than 6 is going to be straight up and down line right here, and less straight across line, and less than is going to be ticked below, just like this. And the last one, x plus y is less than 10. Well, how do you graph that one? What I would do is I'd rearrange this by subtracting x on both sides. So if you subtract x on both sides, you're going to get y is less than or equal to negative x plus 10. And that's easier for me to graph. That's in slope-intercept form. So that line's actually, and it's hard to see because it's off screen, but I'm going to do the best I can. It's this line right here. When it's y is less than that, you shade under that line. So under that line is going to be ticked just like this. Now the question is, where do they all overlap? Well, it's that little area right here. That's why only this area in yellow is shaded. That's where all of those constraints, it forms that shape, because that's where the shaded area. Just kind of like systems of 2 equations, except now we have more than 2. We'll have like 4. But the nice thing is usually with constraints, some of them are easy to graph like this. X is greater than 2, y is greater than or less than a number. Not usually a bunch of these linear equations. So why is this actually useful? Well, there's a reason we actually do linear programming and why it's cool. You have this idea called an objective function. We want to figure out a way to minimize or maximize something. Usually it's profits. We're talking about how to make money, or how much something's going to cost us, or how much time it's going to take. It's something that we can quantify. You're working for a company, or you're trying to plan your budget, and you want to know the right number of things to buy. And you have a certain number of constraints. Well, I can only buy this much, or I can only spend this much time on this. And you have all these constraints, and then you can form a system of inequalities. You can graph it, and then from this graph here, you can create an objective function and just figure out which values, which one's going to be your best choice. That's the point of this. So the objective function, and you'll either be given the objective function, you'll be able to figure it out. So, well, what do you actually do with the objective function? Well, the key point of graphing this is to find what the vertices. These are the key points of the function. And one of the vertices is going to be the maximum or minimum of the objective function. So one of these vertices is going to be your answer. That's the whole point of creating this feasible region. There's vertices here. There's a vertex here, vertex here, vertex here, and vertex here. It's all the corners of the shape are the vertices. So one of those is going to be your answer. So you create this shape so you can find those possible answers, and basically you plug them in. So let's explain that again. How do you do linear programming? So 4 steps, write these down. You got to figure out your constraints, and sometimes that's given to you. Like I say, here are the constraint inequalities. The next thing you need to do is you need to graph those constraints, and you have to shade in the feasible region. So you have to shade feasible region. after you shade that feasible region, you want to write down the vertices of the feasible region. So you want to circle those or indicate all your vertices. Like in that last example, I had 4 different vertices here. So you want to write those down. And then your last step is check each vertex for the objective function and find the minimum or maximum. What do you need to find? It depends what the question's asking you. Sometimes you want to find the maximum amount of profit. Sometimes you want to find the minimum amount of cost. So whatever the question's asking you, this is real world stuff here. This is why linear programming is really useful. But for now, we're just going to work on the mechanics of this. So let's try this one example. I'm going to do all 4 steps right here. What point is in the feasible region maximizes p for the objective function p equals 2x plus y? So I want to maximize this function, and the objective function is p equals 2x plus y. You have to be able to identify those. So let's graph these constraints. I'm going to graph the 2 on the bottom. Those are the easiest first. So x is greater than or equal to 0. Well, that's going to be a line at x equals 0, and that'll be a straight up and down line, right, like this. I'll do it in red. And then when it says greater than, I know I'm going to tick to the right. So I'm going to just tick that a little bit. Now, so I did this one, check. Now the bottom one. Y is greater than or equal to 0. So a solid line again, and I tick above. So okay, so it's going to be positive numbers. Now, check. Let's do this next one here. So I'll do the top one. I'm going to label this 1 and do 1 out here. X plus 2y is less than or equal to 5. So I want to put this in a form that I can graph easily. I'm going to put it in slope-intercept form. So I'm going to subtract x on both sides. And you're going to get 2y is less than or equal to negative x plus 5. And then divide by 2. Everything divided by 2. So I'm going to get y is less than or equal to negative 1/2 x plus 5/2. So I'm going to write 2.5. It's easier with decimals when I'm graphing, at least for me. So now if I want to graph that line, it's in slope-intercept form, so I'm going to start plotting points. The y-intercept's at 2.5, so it's right here. And then the slope is negative 1/2 x, so I go down 1 over 2, down 1 over 2. So I got 3 points right there. I'm going to draw a line between all those. And it says it's going to be y is less than. Y is less than means I shade below. So you already see I got a shape forming, like right? I got a triangle forming right here. But I got one more constraint. So I did the top one. Now I got to do the bottom one. I'll call this, or the second one, I'll call this 2. So that equation is going to be x minus y is less than or equal to 2. Well, I'm going to rearrange that so it's y is isolated. So I'll subtract x on both sides. And I get negative y is less than or equal to negative x plus 2. And then I'm going to divide by negative 1. Everything by negative 1. Since I divide by a negative, I have to flip the sign. So my final answer is y is greater than or equal to positive x minus 2. So, now that's going to be a little tough to graph because minus 2 is off the graph or off the grid. But let's figure that out. Minus 2, let's say it's down here. Okay, so if this y-intercept's down here, and then the slope's 1 and 1, so it's going to be right there, and right here. Okay, I have enough points I can graph that. So that graph of that line is going to look like this. And it says y is greater than, so I'm shading above. Okay, so look, I can see my final shape. And my final shape, it's got to be, between all those lines, it's going to be roughly this shape right here. This shape right here is our feasible region. Now, so I graphed it. I found my constraints because I got them listed. I graphed it. Now, what are my vertices here? So the vertices, I'm going to say vertices. And the vertices are going to be, I'm going to circle in blue. It's going to be these 4. So what are the coordinates of each of those? Let's do the top one. It's going to be 0, 2.5. Bottom one's going to be 0, 0. This one's going to be 2, 0. And this one's going to be 3, 1. So those are my vertices, found them out. Now, I want to find not the minimum because it says I want to find the maximum p. So find it for this objective function. So what I'm going to do is I'm going to, for the objective function, and let's do that, and let's do it in purple. So the function p equals 2x plus y. It'd been really nice if I made a table. Well, I'll kind of make a table here. So I'm going to plug in values the values for x and y and figure out which one's going to be the maximum. So for this first one, you plug in 0 for x, 2.5 for y. So I get 2 times 0 plus 2.5. That equals 2.5. Okay. The next one, you plug it in 0 for both. Well, it becomes 2 times 0 plus 0, which is going to be 0. Okay, the next one's going to be 2 times 2 plus 0, and that's going to equal 4. And the last one's going to be 2 times 3 plus 1, which will equal 7. So which point maximizes? Maximizes is going to be the biggest point. The biggest point here is going to be 7. So the point that maximizes is 3, 1. That's what I'm looking for. And my final answer is 3, 1. So those are the 4 steps right there. We'll be doing more of that in class. Why don't you try it on your own? Pause the video. Okay, what are the vertices of the feasible region? Well, the vertices are right here, 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 and here. So ordered pairs here. The first one, start here. It doesn't matter the order. That's going to be 2, 6. Next one down here is going to be 2, 3. Let's do this one. This is going to be 7, 3. And the last one up here is going to be 4, 6. So there's your answers. Just 4 vertices. Next one. Pause the video. Alright, so let's graph. I'm going to graph. The first thing you want to do is your constraints. And the constraints are here, so that's good. Second thing you want to do is graph. So let's graph what's easy first. I'm going to graph this one first, the middle. Y is greater than or equal to 5. So y is greater than or equal to 5 is going to be right here. It's going to be a straight line, straight across. And greater than means you graph above. So I'll do little tick marks above to indicate we're graphing above. Okay, so that's done. Next one, let's do the one on the bottom. That's also easy. X equal to 0 is going to be a line like this. Since its x is greater than 0, we're ticking to the right side of that line. So there's 2 constraints. Now the last one, so done with that. Last one, x plus y is less than 8. So x plus y is less than or equal to 8. I like to have a y equals form, so I'm going to subtract x on both sides. So I'm going to get y is less than or equal to negative x plus 8. And I can graph that. So plus 8 is going to be a line, is going to be a dot. I'll do that in green. So 8 is going to be my y-intercept right there. And then negative 1x means I go down 1 over 1 for my slope, down 1 over 1. So I graphed a few points there. I'm just going to do a line between them all, just like this. Okay, and since it says y is less than, I am shading below. I'm going to do tick marks below. Okay, and I think we can see there's a region right here, this little triangle. So that's going to be our shaded region. So this is our not our shaded region, it is our feasible region. Let's use the right vocabulary. So I'll shade that in. Now the question is, we got to name the vertices. So that's all I'm doing is naming the vertices. Well, what are my vertices? Boom, boom, and boom. So my 3 vertices here, I'll do the top one, is going to be 0, 8. The next one's going to be at that point, which will be at 0, 5. And the last one's right here, which is at 3, 5. And that's it.